let's look at graphing this function from scratch by hand using calculus. So some of the things we look for are, put some bullet points in here. Symmetry. Well, whenever you've got trig functions, the expectation is it's probably going to be periodic. And indeed this is. It's periodic. Well, sine x has period 2 pi. Sine 2x has period 2 pi over 2, which is pi. So if it was just sine 2x, it would actually repeat twice as often. But since they're combined like this, the thing is only going to repeat with a period of 2 pi. So that's really good to know. Equals 2 pi. And so what that means is, just from that, we only have to plot on the interval from, let's say, 0 to 2 pi. Or it might be smarter to go like from minus pi to pi, and we'll see that that is going to be a little smarter. Because there's other symmetries to look for after all. What about even or odd? The way you test that is you take f of minus x. So this right-hand side, of course, is f of x. And you always just plug in minus x, and you see what happens. So we put a minus x in there. Okay, and now what do we know about the sine function? The sine function is odd, so that minus sign pops out. And the minus sign, of course, goes through the 2 and pops out of there as well. So that's minus sine 2x plus 2 sine x. Now, and then you just ask, there's 3 possibilities. Is that exactly what you started with? No, it's not equal to f of x. Is it exactly negative of f of x? Aha, it is. It's negative of the quantity sine 2x minus 2 sine x. So it's minus f of x. In that case, it's odd. The third possibility is that it's unrelated. It's just not either the exact same thing you started with or negative what you started with. And then there's no even odd symmetry. But this is an odd symmetry. So that means that if I do the part from 0 to pi, so we just plot from 0 to pi in x, then I'm going to be able to rotate that 180 around about the origin, because that's an origin symmetry. And then I can just copy it to get the periodicity. And then, oh, that's not in the subscript or superscript. Oh, just kidding. And okay, and then copy. Okay, so that's nice. That's already reduced our workload. Okay, so what about end behavior or infinities, all that kind of stuff? Well, here it's very simple. This is a continuous function, so there's going to be no vertical asymptotes. And while we're at it, I don't usually make it a separate category, although I probably should. There's no vertical asymptotes. It's continuous, and it's differentiable. This never has any DNEs in any derivative or anything like that. So there's no cusps, there's no corners, there's no breaks, there's no jumps, there's no asymptotes. And then the other thing about a periodic function is that it completely makes pointless any discussion of the limit as x goes to infinity or minus infinity. There's no way it could have like a horizontal asymptote. We know what it does as it goes off to infinity. Whatever we find that it does on 0 to 2 pi or minus pi to pi, it's just going to repeat that over and over again. Okay, so there's really nothing interesting in the infinities category in terms of asymptotes or anything like that. That's fine. That's just less work to do probably. Okay, now what about intercepts and signs? Here's where we actually might get a point to plot. Well, we always plug in f of 0 to get the y-intercept, and that's sine of 0 minus 2 sine 0, so that's 0. So that's the origin. It goes through the origin. That's not too surprising, given that it's an odd function. And what about other x-intercepts? So we're going to set sine 2x minus 2 sine x equals 0. Now, here we have to actually remember solving some trig equations. This is analogous to the example in the book of graphing a function very much like this, and the key is trig identities. If you're stuck on a trig problem, then you're probably missing a trig identity. I say that a lot, and it's because it's true. Hey, that's interesting. That has a common factor of 2 sine x. Whoa, cosine x minus 1. Okay, that's great. It's a product of two things equaling 0, so either 2 sine x equals 0, which leads to x being, well, let's see, when is that? If you go around the unit circle, what angles have the height being 0? Oh, it's any multiple of pi. And the ones we care about most are, remember in here, 0 and pi. Okay, so I'll put a little parenthesis here. 0, not O, 0, pi. Those are the ones that we actually care about. And we know they repeat. Surprise, surprise. We know the whole thing repeats because of the periodicity. Okay, or we've got cosine x equals 1 from cosine x minus 1 being 0. And that, well, you know what? That doesn't give us anything new because that just leads to x. Oops. X equals, that's going to be where x equals 0 or 2 pi or 4 pi. That's 2k pi. And we've already got those covered. These are any multiple of pi. This is an even multiple of pi. So disappointment. Nothing for our labors, but oh well. So basically the intercepts are going to be at integer multiples of pi. So let's look at a sign chart here. Let's put in just a little table, I guess. Actually, let's make it a little matrix. That'll be easier. Okay. So if x is equal to, well, I'll just put in x and then sine. So we're making a sign chart. This is just for f, not for the derivative. And if x is equal, and I'm only going to do it from 0 to pi because I don't only have to do it from 0 to pi. It's going to be very simple. If x is 0, actually it's so simple I hardly need a table. If x is 0, well then we've discovered that it's 0, that the function is 0, it's the origin. If x is between 0 and pi, well, there's no crossings between 0 and pi. We just have to figure out that one sign. Oh, well, we can do that. If x is between 0 and pi, we have to go back to our function and figure out if that's positive or negative. Well, you could just plug in x equals pi over 2. That'd be a fine way to do it, and you'd discover it's negative. There's a little more sophisticated way to do it. Go to the factored form of the function. Always go back to the factored form when you're looking at sines. And then sine between 0 and pi is positive, but cosine is definitely less than 1 because it's never bigger than 1. And so this is going to be positive times negative is negative. Any way you do it, you get a negative. And then if x equals pi, we're back to 0. That's a pretty darn simple sign chart. So on that little region, it's going to go through the origin into the negative y region and then back to the x-axis. Okay. So now it's time for derivatives. Okay. And so let's look at f prime of x or y prime. And remember what f of x is. It's sine 2x minus 2 sine x. So that's going to be, with the chain rule, 2 sine 2x minus 2 cosine. I'm sorry, 2 cosine 2x. Just kidding. 2 cosine 2x minus 2 cosine x. And we want to set that equal to 0 and do a sign chart, etc., etc. Okay, so first of all, we can just go ahead and cross off that 2 there. Okay. Okay. Just making sure. Okay. Alrighty. So how do we solve that? Again, trig identities. So that's going to be, I want to express cosine 2x entirely in terms of cosine. And that's one of the 3 forms of the double angle formula for cosine. That's 2 cosine squared x minus 1 minus cosine x equals 0. So that's a quadratic in cosine x. We don't have to do it this way, but it's a little bit, why do I do that? It's a little bit slicker if we just temporarily say u is equal cosine x, and then we've got 2u squared, and I'm going to reorder it a little bit into the standard order for quadratic, minus u minus 1 equals 0. Does that factor? It does. 2u minus 1, well, let's see, what is it? U minus 1? Something like this. It's got to be plus or minus 1. A 2 and a 1 and a minus 1 and a 1. Does this work? That's 2u minus u. No, that would be a plus u. So this has to switch. And we got it. Okay. So either u equals minus 1/2, or I'll just put a comma here. Just kidding. Or u equals 1. And remember what u was equal to. It was cosine x. So in case you were wondering, back in trig pre-cal, why did we make you solve equations like this? This is why. Okay, so cosine x is either minus 1/2 or 1. And so that means x, remember x is between 0 and pi here. That's all we need for our function, because we're going to do the flip and copy thing, or rotate and copy. What's the mystery angle whose cosine is minus 1/2? That's why I make people memorize your unit circle, because it's really a nice thing to be able to do this in your head. And that's going to be 2 pi over 3. Let's see if I can do it in my head while I'm doing this. That's a 2 pi over 3. Or cosine x equals 1, of course, is where x equals 0. Okay, so there's the critical points. X equals 0, so that's interesting. The origin is not only a place where it crosses the axis, it's also a critical point. We'll discover it's also even an inflection point in a minute. And then x equals 2 pi over 3, 2/3 of the way through this interval that we care about. Those are going to be our critical points. Okay, so now let's make another little matrix for... Okay, I don't really need brackets, though. Okay, so... Did I ever... Oh, yeah. Why don't I just delete those for tidiness sake? Okay, so now x, and now sine of f prime of x. Okay, so what are we going to do? We're going to start with 0, and that's interesting because that's a critical point. That's derivative of 0. And then the next thing we need to watch out for is 2 pi over 3, so I'm going to look at the region between 0 and 2 pi over 3, and then 2 pi over 3 itself, and then 2 pi over 3 up to pi, and then x equals pi. Okay, so we know these are zeros, and we know that now, what about at pi? It's not a 0. It's just because it's an endpoint doesn't mean it's a 0. This is not a place where the cosine was 0. It's a place where the function value was 0. But I don't know. I don't really need to put this in specially. I put it in specially because we know it's a special point in terms of the crossing the axis. But it's not going to have a 0, and it's just going to be the same sign as whatever we see here. Okay, now we actually have to go back to the derivative and plug in values into here, or analyze it a little more carefully. If you plug in values, you could plug in like a pi over 2. Cosine of pi over 2 is 0. This is cosine pi, so that's minus 1, so that's going to be negative. Okay. And then more often than not, when you go through a 0, it changes sign, but that's not a guarantee. Don't count on it. So what's a good x between 2 pi over 3 and pi? 3 pi over 4 would work. And this becomes 3 pi over 2. Now this vanishes. And so minus 2 cosine 3 pi over 4, that's going to be positive. I know I'm doing that quickly, but you guys can do that on pencil and paper or something. So that's going to be plus. Okay, I don't have to write everything out. And then that's going to be plus as well. As it's leaving our region of interest, it is on its way up. And as we saw before, it's crossing the axis. Okay, we're almost done. We just need second derivative. F double prime of x is equal to, let's see, where's f prime? Let's just copy that and modify it. Okay, don't write that down because that's f prime. But now I'm going to get minus 4 sine 2x plus 2 sine x. Okay. And then we want to do a sign chart for that guy, so we want to set that equal to 0. And again, use trig identities. So we're going to have minus 8 sine x cosine x plus 2 sine x equals 0. Can factor out a 2 sine x times 1 minus 4 cosine x equals 0. Okay, so either sine x equals 0, which gives you, on this interval of interest, guess what? X equals 0 or pi again. So both of those crossings of the axis are going to be inflection points. That's interesting. Or cosine x equals 1/4. Now that is not a nice value of cosine. And so that's something where we would actually need a calculator value. That's going to be x equals inverse cosine of 1/4. And what is that? That's about 1.3 radians. Okay, so a little before pi over 2, because pi over 2 would be 1.57. Okay, I'll put a little less than pi over 2. Okay, so that's going to be an interesting value. Now we just need a sign chart for that sucker, and put in our little matrix here. So when x, no, let's leave that in math mode. And now this is going to be sine of f prime of x, f double prime. So at 0, it's 0. At about 1.3, it's 0. And then at pi, it's 0 again. Okay, so 0 less than x less than 1.3. Of course, that's approximate, 1.3-ish. Okay, and then here it's going to be 1.3 less than x less than pi. Okay, so now we just have to plug in values into this quantity up here. So we could plug in like pi over 4. That's definitely in this region. If you plug in pi over 4, you discover this is going to be negative. That's something I'll let you guys work out if you hadn't already on your homework. And then this, for this, I could plug in pi over 2, and that's nice and easy. Here you get pi, that's 0. 2 sine pi over 2, that's 2. So that's plus. Okay, so that is what we need to know. Now, this is where I cheat a little bit, and I'm just going to go ahead and show you the computer graph, but sort of talk about how you could do this by hand. Okay, so remember what you want to do is, let's make just one more table of interesting points, all our interesting points on this little interval x, and I'm going to say y. Okay, you plot the points and then you use the tabular information we have to guide the dot connecting process. When x is 0, oh sorry, y is 0. Oh, let me insert I want a y column, but I also want the y column. Get it? Oh, it's very funny. So there's the origin, and the y is, well, it's the origin. Of course, we want to plot the origin if it's on the graph. But the main reason it's an intercept, but it's also a critical point, and it's also an inflection point. And what kind of critical point is it? We haven't done the flipping process yet, but the fact that it's both a critical point and an inflection point, that already tells us that it's most likely, oh actually we don't know it's an inflection point yet, I'm sorry. It's a 0 of the derivative, of the second derivative. We're not 100% sure it really changes sign there, but I bet it does. The suspicion we should have is that that's a downhill rest, because we know that f prime starts 0 and goes negative there. And the fact that at the second derivative is there, 0 there suggests it's a downhill rest. And we'll see that very explicitly in a minute. And then what are the other points to plot? We had that 1.3 guy. Y is equal to, well, that's going to be a little complicated to plot that. Okay, we might just approximate that or just put it in on the calculator. And then that's because it's an inflection point. Need that in text mode. And at that point it's still decreasing. If you look at the f prime table, all the way in this region it's decreasing. The next interesting point is 2 pi over 3. Oh yeah, let's actually plot what the heck is the y value for that thing. That's the local minimum. Minus 0 plus gives us this local minimum. And if we go all the way up, back up to the function, let's go ahead and copy that down. Some scratch work here. So we're going to have 2 pi over 3. So sine 4 pi over 3, whoops, 4 pi over 3 minus sine 2 sine 2 pi over 3. We could let the computer do that for us, but sine 4 pi over 3 is minus root 3 over 2. Try to do it by hand in the spirit of doing things by hand. Sine 2 pi over 3 is plus root 3 over 2. So then times 2 times minus. Okay, so that's minus root 3. Okay, so that's minus 3/2 root 3. Okay, and that, if we wanted to plot that, that's roughly minus 2.6. Okay. And that's a min. It's certainly a local min, but we're going to discover it's a global min. And then back to pi, that's a 0. And we know that that is an intercept. And we suspect probably an inflection point because the second derivative is 0 there, but we can't be completely sure that it's really a change in sign. Okay, so if you plot those points, oh, go away. If you plot those points, what do you get? Well, here's where I cheat. So if you plot those points, you get this point at the origin. You'd plot that funky inflection point. That you need to do a little more calculation with. It's somewhere in here. You'd plot the minimum, and you'd plot the 0. You'd only get this little bit of the graph. And then what do? Flip all those explicit points. The 1.3 and minus 1.5 or whatever. Flip that up here. That's the inflection point there. Flip them in up to here. Flip the pi comma 0 over to a minus pi comma 0. Now connect the dots smoothly with downhill curving down, downhill curving up, uphill curving up, and then flattening out. Similarly, you get the rotated version of the same shape over here. So that's connecting the dots that we've gotten by finding the explicit interesting points like inflection points and minima and intercepts. Connect the dots with the instructions based on what f prime and f double prime say about the curve. Use the symmetry and then just copy left and right to get the whole graph. You could produce many, many copies of that if you wanted more periods, but that certainly gives you a good picture of what's going on. Okay, whew, that's a big problem, but that's how they go.